evaluate and graph exponential functions. We're going to also use transformations to graph exponential functions. And I think we're going to skip compound interest. Uh, you may recall how to calculate compound interest from high school. It's a formula that looked like A equals P times 1 plus RT, or A equals P times 1 plus R over M to the n negative NT, or something to that effect. So you may recall that, but I think I'm going to skip that for this section. Consider this. Let's say you apply for a job and they pay you this way. For 1 day's work, seems like should be some commas in here, they give you 2 cents. For 2 days work, they give you 4 cents. For 3 days work, they give you 8 cents. For 4 days work, they give you 16 cents, and so on. If you plan to work for 30 days, would you be better off to take this offer or just sign a contract for $1 million? All right. Hold on. Let me see if I do a poll. See what y'all say. Hold on. All right, do y'all see the poll? Would you take the offer, the 2 cents, 4 cents, 8 cents, or would you sign the contract for $1 million? You choose one. I'll show you what people said. This is what people said. All right, so most of y'all thought the same thing, right? Only one person said something different. All right, let's see. So why did y'all choose 2, the second choice?
I chose the first one because it seems like all of it is times two. Like uh 4 times 2 is 8, 8 times 2, 16.
Okay,
So I get
okay.
it keep going up to 30 days. It would exceed over well, well, I didn't feel like doing all the calculations, but I was hoping that it would exceed over $1 million.
You were hoping. Okay, all right. Thank you, Nakiria. All right, others, why did you choose what you chose?
I'm gonna be honest. I feel like it was a trick question. So I said, well, if I divide $1 million by 12 months, I know it's probably gonna be more than that. So
Okay, more than what? More than what? You said if
my bad.
you chose the contract, right?
Yes, ma'am.
All right, for $1 million. All right, let's look at it. It seems like what's happening every day. Nakiria kind of alluded
It's
to it.
doubling.
Doubling. Ah, good. It's doubling. Every day is doubling. So I kind of think of in terms of formulas, which will help, or else we'll just be calculating all day trying to get to 30. So let me think of it in terms of a formula. So it looks like day one. Doesn't it look like it's like 2 to the x power? X x representing what? What does x represent?
The
Uh,
days.
yeah, I would say that x represents the number of days worked. All right. So if we plug in 1, for example, That's 2 to the first, which equals what?
2.
2. F of 2, 2 to the second, which is 4. F of 3, which equals 2 to the third. F of 4, which equals 2 to the fourth, which equals 16. But we want to plug in what number for x?
30.
Let's plug in 30. All right, so you need to get your calculators out for this section, y'all. You really need a calculator for this section. All right, so if you plug in 30, what is 2 to the 30th power? Just give me the numbers. You don't have to read it. Just give me the numbers. You don't have to say million or trillion or whatever. Don't try to figure that part out. Just say the numbers.
I got 107, 374, 1824.
Correct. All right, now we got to figure out what this means. We had 2 cents. Isn't that like 0.02?
Yes.
In terms of money? Y'all get what I'm saying? 0.02, 0.04. So where should we put the decimal here? All these numbers. Where should we put the decimal?
In front of the two?
In front of the, say it again, Zoe?
Say the last two. I don't think they're.
Okay. So 1073741.8.24. Where should we put the commas?
In front of the 4 and in front of the 7.
Okay. So what is this number?
10,737,418 and 24 cents.
Very surprising, right? This is an example. This is an example of exponential growth. All right, exponential growth. It doesn't seem like it should increase like this, but it does. That's why some people, financial coaches, suggest that people around the age of 18, 19, you all should start investing your money, putting your money in like some type of money management account where it accrues interest over time. You keep adding money, and by a certain, I don't know, by the time you're 40 something, you're a millionaire, right? Because you took advantage of that exponential growth, and interest can help you with that. So it's kind of fascinating. You don't think it will accrue that rapidly, but it does. All right, so guess who was the only person that chose to take the offer? Who y'all think chose to take the offer? Only person that chose to take the offer was Nakiria. All right, she's the only person. So you were right, Nakiria. All right, exponential functions are also used to model the world population. Does anyone know what the current world population is?
Like 8 billion or almost 8.
Okay, somebody, me pull it up. Me go to the internet right quick. Let me stop sharing this. And show you the world population clock.
Hey, Dr. Thomas.
Mm-hmm.
Can you tell me how to like put another number in on the scientific calculator or somebody? You know.
Yeah. Okay. What do you mean? What do you mean? Explain
Okay.
it.
So it's a It's just like a scientific calculator. How do I put like we did 2 to the 30th power? How do I put that in this calculator?
Do you see y to the x or x to the y? Something to that effect.
No, ma'am.
Oh no. Can you
Why to
share
the
your video really quick and
yes,
show
ma'am.
me your calculator?
Okay, so can you see it?
Yeah, that's a good calculator. Let's see. Good closer to the screen. Let's see. Huh, you got X. Oh, you got an arrow. That little caret. Okay, let me
What?
show you. Like this. Can you see me? It's like a
Oh, wait a
boomerang.
minute. So I do. Oh, okay. Wait a minute. I think I. Okay.
Mm-hmm.
Okay. Thank you.
Mm-hmm. Mm-hmm. All right. So this is from the United States Census Bureau. All right. So yeah, we're about to hit 8 million, right? We're at 7.8 billion for the world population. A little weird. So about 333 million people in the United States. Um, yeah. So it's kind of weird because we only have 333 million, and look at China's. It's it's the most populous country. That's a lot of people. And India is right behind. So yeah. All right. So moving on. This is an example of exponential growth as well. All right. Let's move on. But yeah, you can look up the world population clock. It's kind of interesting because it tells you the births every 8 seconds and deaths every 11 seconds. It's kind of a little ominous. All right. Any questions so far? All right. Estimate the world population in 2030 using the graphic above. So let's take this old graphic that I've used for a minute now. It looks, I've actually used this graphic right here for about 10 years in my class, but it looks like it's on schedule because 2020, isn't it kind of accurate? It's right here. It's between 7 and 8 billion. So 2030, what would you approximate the world population to be? 2030, if you had to guess.
Like 8.2.
Yep, I'll probably say something like that. About 8.2. 8 point. Yeah, that's good. I like that. All right. So again, examples of exponential growth. I didn't want to bring it up, but that's how they knew that COVID was going to be kind of bad based off the numbers at first, and that's an exponential function. They saw the number of cases, and using that, they could model the number of cases into an exponential function. And they could tell when it would reach so many cases from using math. All right, let's move on. The exponential function with base a is defined by f of x equals a to the x. So what's different about these functions? Notice that x is is an exponent now. It's a little different from what we're used to. The x is an exponent. All right, where a has to be greater than 0. Well, it doesn't have to be, but it is an example of increasing. And a cannot equal 1. Can someone tell me why they pointed out that a cannot equal 1 if it's an exponential function? A cannot equal 1. Why? Why can't a equal 1? Any guesses? You can just guess. To be an exponential function is saying a cannot equal 1. Why can't a equal 1?
It won't be, but I don't know. It won't be multiplied times anything.
Okay.
It'll just be a by itself. Basically.
So it'll be what?
A by itself.
Well, a can't equal 1. It's saying a cannot equal 1, but it can equal other things. Why can't it equal 1 though?
What would it make it 0 or something? I don't know.
It wouldn't be any exponential growth.
Okay. Who said that, Christina? What do you mean by that, Christina? Yeah.
Because anything squared to 1 is itself.
Exactly. Which makes this. Can y'all help Christina out? Because she's doing an excellent job. We would make it what type of function?
Linear? I don't know.
Okay, well, more specifically, what type of function?
Constant?
We're on to something. Constant. All right, because if it was 1 to the 1, it would be 1, 1 to the 2, 1 to the negative 1, it's still 1, 1 to the negative 2, it's still 1. So it's just gonna go, it's not going to increase or decrease. It's just steady across the board. All right, so it won't be doing anything. It's just level. All right, so that's an example of a constant function. All right, let's practice graphing. Well, maybe we need to evaluate first. What does it mean to evaluate a function? Just going back over some things we need to know as 112 students. How do you evaluate? Okay, plug in. What we plugging in for?
F of X.
Specifically X, right? All right, so just X, really. All right, so let's say we have f of X equals 3 to the X. Let's just look at the first one. And I say evaluate the following, f of 2. That one's pretty simple, right? F of 2 is pretty simple. We get 3 squared, which is 9. But what I want you to do is practice on something like number 2 in your calculator. If we plug in f of negative 2/3, I want you to practice in your calculator just to see if you get the right decimal. All right, 0.48 something, something, something. So practice using your calculator because these are going to be homework questions and you're simply just plugging it in your calculator. But if you don't know how to use the calculator, then that's going to be a problem. It's going to be an issue, even though it's really simple. But you do have to know what buttons to push for your particular calculator. So see, can you get to 0.4807498? And when you do, put a number 1 in the chat to let me know that you were able to get to that number. Okay. Okay, very good. Let me stop this poll. All right. Most of you are getting there. All right. So ask questions if you can't get there, because it may be a matter of you putting a parenthesis in for your exponent or something. I don't know. But make sure you can get to that because these are simple homework problems. But if you don't know how to use the calculator, it will be a challenge. All right. Any questions? All right. All right, let's move on then. Let's switch functions. Let's switch functions. Now let's look at g of x equals 0.5x. So plug in 4. All right, plug in 4. Make sure you can get to 0.0625 in your calculator. All right. Also evaluate the function at -2. See if you get to +4. All right. All right. If you got both of those, put a number 2 in the chat for me. Okay. Okay. All right. Anybody have questions about any one of these, 1 through 4? All right. Let's graph now. We know how to evaluate the functions, so we should know how to graph. We simply glean the information from plugging the numbers in. Ken, if you have a question.
Yes, ma'am. I was gonna ask how you put that in the graphing calculator.
Oh, graphic. Okay, so my graphing calculator, let's see. I have, actually, it sort of looks like I use what I saw on Zoe's, actually, because I have like this right here. It's on the far right, and it's under the clear button. Do you see it? And there's a button like this. I don't know if it, we probably don't have the same calculator, so it might be different. You see it? All right. All right, so you can put in the 0.5, for example, that little symbol, and then put the exponent in. All right, let's graph 0.5 to the x. So I'm going to make a t-table over here. All right. Do I have any questions? Okay. All right. Moving on. Let's do a t-table. Let's do x, and let's do g of x. All right, that's 0.5 to x. Since we already plugged in -2, no, we didn't. Yes, we did. We plugged in -2, and what did we get for -2 when we plugged it in?
4.
Right. So let's do -1, 0, 1, 2, 3, 4. We also did 4, which is 0.0625. So what I want you to do is fill out the table. All right. So -1. If we plug in a -1, what do we get?
Let me see.
2.
2. All right. We all in agreement? All right. Plug in 0.
Yes, ma'am.
Okay, good. Plug in 0. We should know that one without plugging it in, right?
1.
All right. All right, plug in 1. We should know that one without plugging it in, right? All right. What about 2, though? 0.5 to the second power equals,
0.25.
yep. And let's do 3. 0.5 to the third power. What is that?
0.125.
Yep. And what I'm going to do now, let's plot this. Where do I go to plot -2, 4?
Left.
To the left.
2.
2.
Down.
Yep.
Up.
Left 2, and then up, right? -1, 2. Where do I go? Where
Left.
do I
To the
go?
left one, and then up 2.
Okay. What about 0, 1?
Up 1.
Origin, then up 1.
Yep. 1, 0.5. How do you do that?
1 and then like half. Go up like that.
Correct. Then 2.25. 2, and what did you say? Somebody said it. All right. For some reason, I can't hear you, but I think you said something like a 4 foot away. And then 3, then it's 0.125. So y'all see how it's getting closer to 0, but it probably is not crossing it. Okay, so this function right here is doing this. It's looking like this. Would you say this function is decreasing or increasing?
Decreasing.
How do you know that?
Is falling to the right.
Very nice. Very nice. So if you trace from left to right, if you trace it with your pencil, it will be going down, which means it's a decreasing function. All right. Very good. Look at this one. Look at this graph of 2 to the x. This one, I already have the points. Is this decreasing or increasing?
Increasing.
Yeah, this one is increasing. It's going up. All right. So just giving you a look at some why. I wonder why these are different, right? That one is 0.5 g of x equals 0.5 to the x. And this one is 2 to the x. All right. What if we made the exponent negative? So let's work on that. Let's do a t-table. X f of x equals 2 to the negative x. What numbers do you want to plug in for x? Doesn't matter. Where should we begin?
-1.
All right. 0, 1, maybe another one, 2. Plug in -1. What would you get?
0.5.
All right. You got 2. Let me look. Let's see. We have f of -1, right? Equals 2 to the -1. What is that?
0.5. Oh no.
2.
2, right? Because it's 2 to the first power, correct? All right. What about 0? What about 0?
1.
All right. What about 1?
0.5.
0.5. What about 2?
1.2.
What about
0.25.
0.25? All right. So let's plot those. Got -1, 2. Let's see how it's looking. 0, 1. 1. Okay. It's doing a little sum here. I feel like I need more points. Give me, what about -2, you all? -2. What is that?
4.
Okay. That'll help us out a little bit. Okay. Make sure we're doing right. One more. What about -3?
8.
All right. So it looks like, is it curving this way? Notice something. Look at this one. Look at the one we did 0.5 to the x, and look at this one. Are we getting the same numbers in our t-table? Did we get the
Yes.
same numbers? Interesting. So -2, 4, all of these are the same. All of these are the same. All right. So that must mean that 0.5 to the x equals 2 to the -x. Let's prove, okay, let me say this. Prove that 0.5x equals 2 to the -x. So I'm going to prove that really quickly. All right. Would you agree that 2 to the -x is the same thing as 1 over 2 to the positive x?
Yes.
Yes.
True, right? Remember we had this rule, if you have a negative exponent, you have to flip something and all that, all right? Would you agree that this is the same thing as 1 over 2 all to the x power?
Yes.
Right? Because there's a rule that says you can split this up as 1 to the x over 2 to the x. But 1 to the x will always remain 1, right? All right, 1 to the x. We discussed that a little earlier. 1 to the x will always be 1. And 1/2 is 0.5, correct? All right. So we just proved that 1/2, well, 0.5 to the x is the same thing as 2 to the -x. All right, let's move on. So what are we saying? The graph of f of x equals a to the x right here. If a is greater than 1, it's going to look like this. If a is between 0 and 1, it's going to look like this. For example, the 0.5 graph, 0.5, when a was 0.5, it looked like that. It was decreasing. All right. On the right, if we graph, for the 2 to the x, that was a was greater than 0 here, so it was increasing. So that's going to happen every time a is greater than 1, and you have a to the x power. That's an example of exponential growth. When it's increasing, that makes sense, and when it's decreasing, is an example of exponential decay. All right. Notice the similarities between the two graphs. What are the same? What if you compare these two graphs? That's why I put them right side by side. What are the same? They have the same what? Just call it out.
Horizontal asymptote.
Yep. They have the same horizontal asymptote. Y equals 0. What else?
The same
Domain
domain
and
and
range.
range.
Same domain and range. One more thing.
Both of them have the point 0, 1.
What is that point called? Somebody other than the carrier. What is that point called? 0, 1. Give me a nice math term. All right, 112. You got it. You got it.
It's the y-intercept.
It is a y-intercept. Very good. Y-intercept. So where your graph crosses the y-axis, that's called a y-intercept. That's when x equals 0. If it crosses the x-intercept, well, if it crosses the x-axis, is called the x-intercept. All right, moving on. Here's an example of the difference between 2 to the x and 2 to the x minus 1. What is the difference? So let's look at the one in purple. That's 2 to the x. Similar to what was done already. 2 to the x. What happened with the black? Give me some nice math terminology. Is it 2 to the x minus?
A vertical shift down.
Very good. All right, vertical shift down. How many units?
1.
Yep. Shift down 1 unit. All right. Remember, that's called transformations and translations and shifting. All right. What do you think would happen with if we put a negative in front of the 2 to the x? I don't know. Let's see. All right. So let's graph this one. All right. Put another color here. X and f of x. What numbers you want to plug in? Let's just go with -2, -1, 0, 1, and 2. All right, plug in -2. Tell me what you get. I'm plugging in with you. -2. Anyone?
-0.25.
-0.25 is correct. All right. Any questions about it? All right. Someone other than the carrier. Tell me what we get when we plug in -1.
Negative 0.5.
All right, Tanaya, I think that was you. All right, correct. Let's move on to 0. Someone other than Tanaya and the carrier. When you plug in 0, what do you get? That's a rule to this one. Yeah. It's a, huh? All right. Is it 1 or -1? Which one
negative.
is -1? All right, because -2 to the x is the same thing as like -1 times 2 to the x. So -1. So if we plug in a 0, we will get 1 for this part, but when you multiply it times -1, you get, well, yeah, -1, you get -1. All right, let's plug in a 1. What do you get?
-2.
Okay. What about 2?
-4.
All right, let's plot. -2, 0. Okay. Right here, maybe. And then -1. Okay. All right, it's doing this. So it looks like it's, if we compared it to this, what do you think it's doing? All right, that's 2 to the x.
Reflecting over the x-axis.
Oh, very good. Very nice. Reflection about the x-axis, you say. Okay. Nice. So don't throw away the information you learned about transformations. That's what the point I'm trying to drive here. Some of these you can kind of look based on what you learn about shifting and reflections. You can figure out what the graphs are if you had to choose a graph for one of them on your homework. All right. Let's move on to something called the number e. Have y'all seen this number before? E to the x, for example. Not sure, but it's approximately 2.7 something, 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 something. Sort of reminds you of another number with a symbol. What number is that? There's another
Pi.
symbol. You're right, pi, which is approximately what something, something, something.
I think it's like 3 point something.
Mm-hmm. 3.14. All right. So this is used in applications involving growth and decay and in nature. It's approximately 2.7. So again, it looks like this on the right. That makes sense because 2 to the x, if 2 to the x looks like this here, then 2.7 is probably not going to be that much different. A is greater than 0, so we know that it's going to be an increasing function. All right. I want you to locate the E on your calculator, the E to the X. See if you can find the E to the X. You might need to find the LN button. That's called the natural log. And then if you find the LN button on your calculator, you should see the E to the X above that button. All right, put a 3 in the chat if you found the E to the X on your calculator. All right, so that's what I want y'all to use. Please don't try to put 2.7 something, something, something in. It's not going to be accurate. All right, because it's so many numbers, it might throw the rounding off a little bit if you try to plug in all the decimals. Plug in E and it'll be better. So let me just throw a random E to the something and see if you get the right answer. So if I say, what is E to the, I don't know, -5? What is that? I gotta do it too. E to the -5. Give me 3 decimal places.
0.0.
0.0. Say it. We would say it again because I think you're going in and out, Kenneth. I don't know why, but you're going in and out. 0.0. Did y'all say 0.7? Okay, good. It's muffled for some reason. All right, good. I just want to test that out. Let's see how many people put a 3 in. Make sure y'all.
Dr. Thomas, I see the little E button on my calculator, but when I put in -5, I didn't get that.
Oh, You see the E? Does it have an E to the X on it?
Yes,
To
ma'am.
the
It got
X.
like E, and then it has like a little blank box for where you should put in like the exponent.
What did it give you when you plugged it in?
6.7.
Oh. Hmm. I don't know why that's throwing yours off. Zoe, you have a question?
Yes, ma'am. Did we round up or something?
It may have been.
Cause I
It
got
may have been.
0.00 points. I got 0.006.
Quite a
0.006. 0.006. Okay, you say you got 0.006. What else?
737.
Okay. Yeah, I asked for 3 decimal places. What
Oh,
does that mean? I say round to 3 decimal places. That means I only want 3 numbers after the decimal.
okay. And so you rounded that number up.
Uh-huh.
Okay.
So if I say round to 4 decimal places, I want to see 4 numbers after the decimal, but you round if that number to the right is 5 or higher, right? You move that number up 1. All right, so that's why it's 0.07. Now, Nakiria, E to the -5 Would you agree is 1 over e to the 5th? Would you agree? All right.
Yes, ma'am.
So if that's true, and when I put in e to the 5, that's like 148 point something, something, something. So I just want you to do it the other way and see what it gives you. All right. I don't know why it's doing that. You're going to have to figure that out, though, just in case it pops up on the homework. I'm not sure.
Sometimes you have second button, like that's for the other operation.
Oh, you're right. You may be doing LN. You need to do e to the x. So it's very good observation. You need to do second LN. So if it's not on the button itself, you have to hit the button at the top, second, then hit LN. All right, let's move on to the last concept of today, which is using a one-to-one property. So let's look at this. 9 equals 3 to the x plus 1. If I say solve for x, of course, you may not know what to do, but could you figure it out by just guessing what x is? Meaning, we know we want these to equal each other. So we know we need to plug in an x that will make the right side equal 9. If you had to guess, what is x? What would your guess be?
1.
Very good. Because x plus 1, if x was 1, it'd be 2. 3 squared is 9. All right, but I'm going to show you how to solve these mathematically because they're not always going to be that easy. All right, first step, get the bases to be the same. Okay, step 1, I don't know, that's good grammar. Get the base to be the same. All right. So the bases here, we have a 9 and we have a 3. We want both of those numbers to be the same number. Can't I make 9 3 to something? What can I make? How can I change 9? 3 to the what power?
3 to the second power.
Correct. All right. So we first start with that step. Once the bases are the same, set the exponents equal each other. All right. What's the exponent on the left? 2, right? And on the right side is x plus 1. Yep. How do we solve for x? Now we have 2 equals x plus 1. How do we solve for x?
Subtract 1 from both
Subtract
sides.
1 from each side.
That's simple as that. Therefore, x equals 1. All right, that's how you solve it. All right, and you can always check by plugging in this 1 into the original. All right, you can check answer. All right, we're going to move on though. Let's look at this example over here. 8 equals 2 to the 2x minus 1. Our bases are 8 and 2. They're not the same. We need to get them to be the same. How can we get them to be the same thing?
2 to the third.
2 to the third power.
Very nice. 2 to the third equals 2 to the 2x minus 1. Now that our bases are the same, we can get rid of the bases and set the exponents equal each other. All right. How do you solve for x?
Minus 1 on both sides. I mean, plus 1 on both sides.
All right. We're going to add 1. So we have 4 equals 2x. What else?
And then divide by 2. Divided by 2.
Divide by 2. X equals 2. All right. You can always check again. Always check. All right. You can plug that in into the original to see if the left side equals the right side. Let's go to this example, 1/2 to the x. All right, this is a little bit more challenging, but I'm going to show you what to do so that it's not. All right, 1/2. Would you agree that 1/2 is the same as 2 to the -1 power? Would you agree that 1/2 is the same thing as 2 to the -1?
Yes.
Very nice, very nice. Now, there's a rule when you have exponents right next to each other like this. What's the rule? What can you do with these exponents right here?
Multiply.
Correct, correct. So this is the same thing as 2 to the -x. And we can change this 8. Didn't we just do this? 2 to the what? 8 is the same thing as 2 to the third. Our bases are now the same, right? So we can get rid of the bases and just set -x to equal 3. What should you do now?
Multiply by -1.
All right, or alternatively, you could have done what?
Divide
Both
by
work.
negative.
Divide by -1. All right. Normal people say divide because they consider that to be -1 times x, but it doesn't matter when it's negative like that. So both of you are correct. X equals -3. All right. I want to see if you can get this one done. 1/3 to the -x, slightly different, to the -x equals 27. And I'm going to give you 2 minutes. All right. Direct message me what you think the answer is. Don't send it to everybody. Find my name and send it to me. All right. Okay. All right. We're going to get to the bottom of it. We have a couple different answers. So we're going to get to the bottom of them. See which one is it really? All right. Let me begin. 1/3 is the same as what? How can that be written?
3 to
Three
negative
to
1.
the -x.
-1, right? Okay. So first we're going to write it like that. 1/3 is the same thing as 3 to the -1. All right. And then again, what's the rule with the exponents? We can do what to the exponents here?
You can multiply them.
Multiply.
So what is -1 times -x?
X
X. All right. And 27 is 3 to the
third.
third. So simply x equals 3. All right. Let me take one from the book. All right. Because I see one that says solve, use the 1-to-1 property, e to the 3x plus 2 equals e to the 3. Question, are the bases the same?
Yes.
Yes.
Yes. So what are we going to set equal to each other?
The exponents.
Yep. 3x plus 2 equals 3. Now what?
Subtract 2.
Yep. 3x equals 1. And then
Divide by 3.
divide by 3. X equals
1/3.
1/3. 1 more for the road. All right, because this is a little bit more challenging. What if we had solve
Oh,
E questions? You have
oh no,
questions?
no. I'm sorry, Dr. Tom.
Oh. All right. E to the x squared minus 3 equals e to the 2x. All right. I'm going to let you think about it for a couple minutes. Work on it for a couple minutes, and then I'll work it out. Okay. Okay. Christina and Alicia. All right. I'm going to go ahead and solve it. All right. What is the first step? Tell me what the first step is.
Set
Setting
them.
both to each other. Some each other.
Yep. So we're going to set, okay, that's not going to work. X squared minus 3 equals 2x. This is a crucial step. What did you do next?
Put the x terms on one side.
Put the what on one side?
The terms with the
You
x.
put everything on one side, right? So we're going to move the 2x to the left side. I'm going to put it in descending order. X squared minus 2x minus 3 equals 0. So recall the 4 steps we talked about before in the class. Put everything on one side. Set equals 0. What's the next step?
Factor.
Factor. X, what are the factors?
-3 and 1.
-1 or +1?
+1.
All right. So we said x minus 3 equals 0 and x plus 1 equals 0. What are the solutions?
X equals 3 and x equals -1.
Correct. 3 and -1. So we actually had 2 solutions there. You could always check, you guys, just in case you want to know. You can, if you're a little hesitant about the answer, you could have plugged in 3, right, into the original to see if the left side equals the right side. So we'll get e to the 9 minus 3 equals e to the 6. E to the 6 equals e to the 6. So I just plugged in a 3, and you can do the same thing for -1. But that's all our time. If you want to take a look at the YouTube video here, you can click on it. If you open up the document in Blackboard, you can just click on the link. It talks about basically coronavirus and how this person kind of predicted it based on the number of cases last year.